All right. So let's go ahead and dig slightly inside the Euler forward method. So this equation, x dot is fxt. So how do I solve this equation? Well, you start with x0, then go to x1. And where do I compute the slope? F, which is at x0. Okay. And I go ahead, right? And this is straightforward. Then I can go to x2 given x1 and so on. At nth step or n plus 1th step, I get xn e plus delta t f xn tn is xn plus 1. Okay? So we can just write a loop. Okay? And this is also called explicit scheme because my answer at xn plus 1 is the explicit function of xn. So right hand side also only involves xn. Okay, so this is called explicit. Okay, it's pretty straightforward. So let's look at how to write the code. So I have this function. I mean, I want to integrate this. X dot is minus 100x. I know the exact solution, but still I want to do by numerical scheme. So this by definition of the function, and Euler explicit is f t init t final dt initial condition. Okay. Now number of steps is here, and I discretize t like that in n steps. Then initialize x. So x0 is init condition. So by the way, first order equation has only one initial condition. Okay. So only one initial condition. So x0 is init con, and now I loop. So xk plus 1 is xk plus f sk tk times dt. Just straightforward. No? So and I return t comma x. So I get an array t and array x. So I know that what are x. So I also keep the history. It's not that you give only at given time what is position. You have all the position at all the times, and then you can make a nice plot. So I start with initial condition 0. I go to t final 1. dt I use 0.01. T initial condition is 10. Start with thing, and I call this. So the function looks like that. So we know the answer. X dot is minus 100x. So x is x naught e to the power minus 100t. So it's a function which is decreasing in time. In fact, exponentially decreasing in time. So for all such functions, it is good to plot in a semi-log scale. Okay. If I plot in linear scale, it's going to go down like that. Okay. But it's not clear. I mean, is it 1 by x squared, or exponential? So if you plot in semi-log scale, you'll get a straight line, right? I mean, everybody knows that log x is log x0 minus 100t. So slope of this line is minus 100. Okay, in log scale. So if I make a log, this is minus 1 and this is minus 3. But it's written like 10 power minus 3. But it's really, beginning is log. Now, yeah, blue is the numerical curve and red dash is the exact curve. Exact is this one. And they are on top of each other. Okay, so my numerical scheme is working fine and is great. But of course, this is a simple equation. Anybody can solve it. Then you say, well, what's the use? Numerical computing is useless. But not so. We can. I show you more complex example. Let's look at z dot is minus I pi z. Okay. Now z is complex, because this I is the square root of minus 1. And this too has exact solution. Zt is z0 e power minus I pi t. Okay. And if I solve by the same method, that method will work for complex Z as well. Okay. So that's the beauty of Python. We can dump in any data type as long as your operations are compatible, it will run. And the same code will work for complex Z. So I start with the initial condition, okay, and it turns out it just keeps going outward. Huh? So this is just going outward. You can see the arrow, no? I mean, it's just going out like that. But my real solution is what? Is it outward going? The real solution is not that, because you can look at from this, mod of zt is the same as mod z0. Okay, so real solution is just if initial condition, it should have been just circle like that. Okay, it's cos t plus I my cos pi t minus I sin pi t. So numerical solution, I use a finite delta t, and this is what is coming. Okay, my code has no problem, but it turns out the numerical method itself has a problem. Okay, I'll do it. I'm going to show you in a while. Numerical method is any finite delta t will show you that is spiraling outward. Okay, so this one has a problem. Euler forward is no good for this. You should not use Euler forward. Don't use it. If your equation is like this. Now, how do I know which equation I should use Euler forward, which I should not? So I will tell you. You just have to wait for 5 minutes. Okay, now let's look at slightly more complete equation. This is that equation. It's a non-linear equation. So far the right hand side was linear in x or linear in z. So, but here right now I got non-linear in x. Exponential minus x is not linear in x. No? When you can just plot it, it is exponential is that. Okay. Now it turns out you can solve it exactly, no problem. Any 1D equation can be solved analytically. Okay. You may have very complex expression, but it can be solved analytically. But let's do numerically. It's just straightforward. I have the code. I just put initial condition and just run it. And it turns out this decreasing function, and in fact, it goes to negative value at t equal to 2, and it's like that. Okay. Now here too, the numerical solution and the exact solutions are matching on each other. Okay, they're on top. I'm not writing the exact solution, but I will share the notes, and you'll find that. Okay. I'm not telling you dt. I mean, dt, I think is 0.01, but is there in notes? I forget right now. Okay. Now, what's the error in this scheme? So, let's do a Taylor expansion of x n plus 1. What is x n plus 1? So, x n plus 1 is, I do Taylor expand around Tn. So, it is xtn plus delta t x dot plus delta t squared to x double dot, like that. Okay. Now, so x dot is f, no? X dot is f. So here, this is the term which is here and like that. So, what is the forward scheme? Euler forward scheme? Euler forward scheme is only this. Correct? Euler forward scheme ignores this part and higher order terms. Okay, xn plus 1 is xn plus delta t f xn tn. So error is what? Error I defined, my definition is v or value actual minus value numerical. So actual value is everything, equation 37, and numerical value is only this. So this is error. This and onward is error. But we say, well, higher order terms are small for delta t small. So my error is to leading order is in fact is approximate. The approximate is this object. Okay, df by dt is x double dot. Okay, so error is delta t squared in each step. Every time step we have error of delta t squared. Okay. Now I go from T0 to T final. By the way, please remember one thing, that my f is positive for a function like that. Okay. So my error is my projected value is the actual value is here. No, so if I had function like that, then f is positive. It's a curvature. F is a curvature really. X dot everything. So my actual value is this one, and my projected value is actual is larger. So projected. So these error. This is basically the error. Now, if I go from T0 to Tf, what happens to the net errors? Okay, every time step I am getting this error. Now, will it be additive or will it be okay? So I remember I had made this statement that systematic errors you can write n times epsilon n is the total error, or is it epsilon total equal to square root n times epsilon n? Okay. Now, what do you think? Systematic or random? Okay. Here, of course, it depends on the function. I mean, it depends on f. But in general, Euler will keep adding up. Okay. So at this point, if the function, it just depends on the function. If function continues to be rising, then the error will keep getting accumulated. Okay. So it depends on f. But in general, if I want to make an estimate, I'm going to use this formula, because I want to be safe, and if function is slightly monotonic, it's going to be additive. Okay. Of course, if f is fluctuating, then, or actually fluctuating, then of course ODE will have its own problems. But if it is kind of oscillating, then there can be some cancellations. Okay.